Hello everyone, welcome to my channel. Today I am going to talk about Couette flow analysis, velocity profile and shear stress from Navier-Stokes equation. Here that fluid is flowing in between two parallel plates, upper plate is moving and bottom plate is fixed. Now here is the problem statement. So Couette flow configuration. So two infinite plate separated by distance 2h. Upper plate y is equal to plus h. Here this is the central line and y start at 0. So upper plate at y is equal to plus h moves with a constant velocity u in x direction. So fluid flow is happening at x direction. Lower plate at y is equal to minus h is stationary, no slip condition. So this bottom plate is fixed. So here as plate is fixed or stationary, so velocity adjacent to the wall is 0. And fluid is incompressible, Newtonian fluid with constant properties, means rho and mu are constant. And here that fluid flow is steady state, means dou by dou t of something is equal to 0. No pressure gradient, so dou p by dou x is equal to 0 and no body force acting on the fluid. So body force is equal to 0. So means here no body force acting here because this is the horizontal flow is happening, means plate is horizontal and fluid flow is happening in x direction. Now here are the objectives. Derive velocity profile uy from the Navier-Stokes equation. Determine shear stress distribution tau y and analyze the flow characteristics. Now here is the geometry and coordinate system. I am already talking about that. So it is that uh, fluid is flowing between two parallel plates. One plate is moving and another plate is the fixed plate, and fluid flow happening in x direction. There is a no flow in yz direction, means if you consider that velocity component x, vy and vz, so only the x direction fluid flow is happening. So that is this term is there. Other term vy is equal to 0 and vz is equal to 0. Now here are the physical assumptions. Steady flow dou by dou t is equal to 0. Fully developed properties depend on only on y direction, because here if you take 2 points here and here in same line, so velocity actually not changing because it is a fully developed flow. So velocity is changing in y direction. So properties depend on only y direction. So that's why Vx is Vx function of y, means Vx is function of y. And the plate is infinite plate, so no variation in z direction. So dou by dou z is equal to 0. Incompressible fluid, so rho is constant and no pressure gradient, dou p by dou x is equal to 0. Now velocity field simplification. So u is uy, only x component, function of y only, and v is 0, w is equal to 0 because no y component, no z component. And boundary condition, so u is equal to minus h, so plate is fixed, so velocity is 0. Here u plus h, that plate is moving, so velocity is u, capital U, that at u plus h, capital U. Now starting point Navier-Stokes equation. So first we have to take that continuity equation. So dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0, and momentum equation. So x direction, y direction and z direction. So x direction rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou w minus dou p by dou x plus mu nabla square u. So here nabla square means that dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So if I write that, so mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Similarly this term, so all that u term become v and here all u term become w. So you can write here, so mu dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. Similarly here mu dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. Now here we already know that v is equal to 0 and w is equal to 0. So x direction and y direction momentum equation, all term will be 0. Only x component momentum equation we will work on. Now starting from the continuity equation, so dou u by dou x plus dou v by dou y plus dou w by dou z. So v is 0, so this term will be 0. W is 0 because no velocity in y and z direction, v and w will be 0. Now automatically dou u by dou x is equal to dou u by dou x is equal to 0. So that will be actually u is equal to u of function u of y, means that u that is a function of y only. So now after getting that, so here, so now if I plug that continuity equation, means this term will also be 0, this term will be 0, this term will be 0. So finally that continuity equation automatically satisfied. Now here we are taking the x momentum equation because other momentum equation is 0 because v and w is 0. So now we can write that this term, so that is mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Now here that dou u by dou t is 0 because steady flow, so this term will be go away. And here dou u by dou x, that is we got from the continuity equation, so that is also 0. V is 0 means this equation is 0. W is 0 means this equation is 0. And here pressure gradient is no pressure gradient, so that will be 0. Now here that u is u of y only. Okay, so this term will be 0 and this term will be 0. Only this term will remain. Okay, I'll coming back to that. So now here everything is there. So only this is 0, this is 0, this is also 0, this is also 0. So only u is u function of y. So only this term will be there. So only this term will be there. So this term as u is function of y only. So partial derivative become the ordinary differential equation. So we have only rho is equal to 0. So here everything is 0, everything is 0. So mu dou square u by dou y square is 0. So we have this term only. Now from here we have to do the integration. So this is the governing differential equation for Couette flow. So physical, what is the physical interpretation? The second derivative of the velocity with respect to y is 0, which means the velocity gradient du by dy is constant throughout the fluid. Now this is our starting point. Okay, now if I first integrate, so du by dy is equal to c1, so that is constant. Second integration, u of y is equal to c1y plus c2. Now we have two constants c1 and c2. We have to find out that c1 and c2 by using boundary condition. So now, so we got this. Okay, so and here general solution is u of y is equal to c1y plus c2. So this is a linear profile because y is equal to mx plus c. It's like that. Now that boundary condition. So at y this minus h. So no slip boundary condition means u is 0, and u at y is equal to plus h, u will be capital U. So as the plate is moving, means top plate is moving, so velocity is u. Now if I plug the boundary condition y 1, so that will be u minus h is equal to 0. So we will get c1 minus h plus c2 is 0. So from here c2 is nothing but c1h. Now second boundary condition. So here we put that u plus h is a capital U. So c1h plus c2 is u, and here c2 will be c1h. So c1h plus c1h means if I plug that c2 is we got that c2 is c1h. So if I plug in this equation second, so that will get 2 c1h is equal to u. So c1 will be u by 2h and c2 will be u by 2h. So into h. So that will be u by 2. So now we plug C1 and C2. Finally, we will get uy is equal to u by 2 1 plus y by h. So this is the linear profile we get. So that is the linear distribution of the velocity profile. Now if we plot that, so it will be like that. Okay, so velocity is increasing and we will got the profile. So u is equal to u by 2, capital U by 2 into 1 plus y by h. Now we can also calculate the shear stress. We know Newton law of viscosity, tau is equal to mu into du by dy. So if we plug and if we do the derivative, we'll get du by dy is nothing but u by 2h. So that is also constant. So finally, if we plug that du by dy, so we'll get tau is nothing but mu u by 2h. So that is constant. So shear stress is constant throughout the fluid. Now here if we draw that, so it will be the linear profile means constant. Okay, so parallel to the y-axis. Okay, so tau is equal to mu u by 2h is equal to constant. So finally, final result is velocity profile u is equal to u capital U by 2 1 plus y by h, and shear stress distribution tau is equal to mu u by 2h is equal to constant. So that's it about Couette flow. Thank you.